Hello everyone and welcome to Energy and Environment. This is Chapter 2, Part 2, Production. I wanted to look just very briefly at some of the basic production methods and concepts associated with our three fossil fuels. The first fossil fuel is coal. Now coal has a distinction. First of all, it was one of the main fossil fuels that we started to use and we've been using for hundreds of years. It's also the one in the United States that we have the most proven coal reserves. And by that it means what we can not only find, but what we can actually extract and use. When you look at coal and coal mining, the first thing you think about is the grade or rank of the coal, which relates to the amount of carbon content, aka fuel, and the number of contaminants. In other words, it's a concentration such that you're going to get your coal, but you're going to have to first process it to sift out things like metals, arsenic, clays, so on and so forth. When you start to then talk about coal mining, there are a number of methods. And which method you use depends on the geology. Sometimes it depends on the company. In other words, what are they capable of doing? And it also depends on the grade in terms of how much processing has to be done. Obviously, the shaft mine has the least amount of disruption on the overall structure because you just have minimal on top and then you mine and dig out below. Some of the big things, however, is of course now you're creating large gaps in your rock and this can destabilize the area. Your slope mines and your drift mines are compromises. In other words, instead of just going straight down to the coal, a slope mine has to dig through more overall rock, but you're still containing most of the work underground. A drift mine has some underground, but it also will involve either starting on the edge or side of a mountain or digging to that point. And then surface or pit mining is the all out, we're scooping everything up, we're crushing everything up, we're processing it and taking out what we want or need. Petroleum, of course, is going to use slightly different methods because now we're talking about a liquid. Usually what happens is you go to an area, you drill a couple of exploratory wells, and you see what the grade, purity, and pressure is. Then you will go and fan out from that area to try to get a determination of what's the amount or volume. In other words, what's the proved reserve. If it meets the needs and standards of the company that is doing the exploration, then they will begin to sink wells. And what type of well depends again on what is the oil like underneath, are they on land or in water, and other considerations. Now usually a basic well, because it is a liquid and it's been under pressure, the well provides a space or opening so that material can flow through that opening. Usually, however, this will only happen for about 70% of the oil that is down there. Again, it depends on the geology of the area. So often what happens over the lifetime of a well is you then go into secondary and tertiary methods, which now take more energy because now you have to pump liquids, gas, or sometimes they use steam, and that increases the pressure the system so it then forces the rest of the oil out. I'm not going to really talk a lot about tar sands or oil shale right now, but something to keep in mind. It takes about 2 tons, remember a ton is 2,000 pounds, of material to produce 1 barrel of oil. Going back to chapter 1, do you remember how many barrels of oil an average United States a person in the United States uses on average per year? Yes. So multiply 2 tons times 50 times, let's say, 310 million people in the United States, and you're starting to talk about disrupting quite a large piece of the environment. And this is just an example of some of the different tiering structures that can be used for underwater drilling. And here's an example of a well. When you put that basic pumping mechanism down, you also have to have a series of secondary structures, such as the casing, the tubing, your pump within to help bring that liquid up to the surface, depending again on the pressure. Something important to note with oil is that when you pump oil out of the ground or the petroleum, it's usually what we call crude oil, which is a very base hydrocarbon concentrate. To get all of the other various fuel sources that you hear about, gasoline, kerosene, heating oil, jet fuel, all the different levels, you take this base crude oil and you begin to heat it. And it turns out that different forms or different hydrocarbons have different boiling points when they convert from liquid to steam. And so what happens is as you start to heat, you'll have the different materials that actually will boil off, and at each point these particular materials can be condensed out. This whole process of converting the crude oil that comes from the ground, refining it to one of the forms that we're going to use, is called fractal distillation. And it is a very important process because, again, each of these different pieces in our society use different forms of petroleum. So that's another place that we have the lost energy. Remember from chapter 1 where we have all that energy coming in and over 50% is lost? This is one example of why that occurs. With natural gas, again, now we're moving from liquid to gas. You have to take into account that because you're moving a very volatile material, there are not a lot of methods and systems in place that will help to promote that. Because of that, gas exports do occur, but they're very limited compared to oil and coal. When you look at natural gas, again, just like with petroleum, what comes out of the ground is not exactly what you're going to use, and it does have to be processed. Again, just as with coal and you have contaminants natural gas, and those have to be removed to a very specific purity level that's been set by different governments and different systems. Because again of the volatile nature of gas, usually these processing plants are set near where the actual material is drilled from. A method of extracting natural gas has recently come into light. It's actually been around since the 1940s, but it wasn't always economically viable until, again, as our technology has increased and developed. And this is the concept of hydrologic fracking. Now, fracking itself has actually been around even longer because it is used in other places besides natural gas extraction. It is used in some cases to help open up well systems. It's used to do different management with certain environments. So it's been around. But again, here we're starting to talk about doing it on a much larger scale and with much higher pressures, and also the fact that usually what happens is you mix in sand and chemicals, and there's the key chemicals that are then injected and they create small fractures. You are fracking or fracturing the rock. And a lot of the issues come into play that this liquid treated with these chemicals is now going to begin to leak into the rock, and you're opening up new conduits. So this will change other systems, such as groundwater systems. If you take a look at this image, and this is a very simplified image, you see that you have to have the water delivered, you have to mix the sand and water, and then you inject this. This actually, like I said, it causes the shale to fracture. Why? Because then it's going to allow gas that has been trapped to now flow, and it comes back up to the well, and then it is taken out. The recovered water is stored as waste, and the natural gas is separated and piped out. This is a very interesting image because again it kind of puts everything together and shows how sometimes it's not the fracking itself that is directly doing the potential changes in contamination, but the fact that now that you have these additional structures that weren't there before, systems that you had set up for the non-fracked environment now may suddenly develop leaks. And so there's been a lot of secondary issues associated with fracking. All right, next up, we'll look at the economic and social environmental impacts.